Right. So very good morning to you all. I welcome you all for today's EMF session. We have been discussing on EM wave propagation in different media. In my last few classes, I have discussed about EM wave propagation in free space, EM wave propagation in lossless dielectric media, EM wave propagation in lossy dielectric media, and EM wave propagation in a good conductor. Right. So let me recollect the things which I have discussed in my last class. So EM wave propagation in a lossy dielectric media, as usually we have taken the Maxwell's equations. Maxwell's equations are modified according to the characteristics of the media, and we have equations 1 to 4. So taking equation 1, applying curl on both sides, and simplifying, we'll get wave equation, right? So in wave equation, gamma is one parameter which is called propagation constant. So gamma square is equal to minus omega square mu epsilon plus j sigma omega mu. So that is the expression for propagation constant, right? And gamma square, gamma is alpha plus j beta, and where alpha is attenuation constant and beta is the phase constant. Substituting that and simplifying, we will get alpha square minus beta square, which is in equation 7. We have alpha square minus beta square. If we can have alpha square plus beta square, we can determine alpha and beta very easily. So to get alpha square plus beta square, taking equation 6 and applying mod, right? So as shown here, so applying mod like this, right? So mod of a complex number or magnitude of a complex number is equal to square root of real part square plus imaginary part square, right? So here that is what we have done, and from this we got alpha square plus beta square. So equation 7 and equation 8, solving equation 7 and equation 8, we will get alpha and beta. So alpha and beta equations are as shown in figure in equations 9 and 10, right? So this is how we can define wave propagation in a lossy dielectric media. In a similar way, a good conducting media can be defined directly from the expressions of alpha and beta, right? So here the good conductor characteristics are sigma is equal to infinite for both lossy dielectric media, for both lossy dielectric and good conductor, sigma not equal to 0, right? Sigma not equal to 0. So therefore expressions for alpha and beta, you can take these equations, right? So alpha and beta, you can take these two equations and applying condition for a good conductor, we have a condition. So this condition, right, sigma by omega epsilon is very much greater than 1, and substituting this condition in the above equations, and we will get alpha and beta, right? So here it was found that alpha and beta are the same for a good conductor, right? So which is equal to square root of pi f mu sigma. And here I have given a comparative table comparing alpha and beta, attenuation constant and phase constant of all four medias, right? So free space, lossless dielectric media, lossy dielectric media, right? So I have given a summary right here. So alpha for free space and lossless dielectric media, alpha is 0, and for lossy dielectric and good conductor, alpha not equal to 0, right? And also we have derived the expression for intrinsic impedance, right? So derived the expression for intrinsic impedance by taking one of the Maxwell's equation here. So equation 1 is one of the Maxwell's equation in phasor form. Expanding equation 1, right? Expanding equation 1, we will get this one, right? And find out the determination and equate left hand side terms and right hand side terms. So here you can see on left hand side ax, ay, az, and on right hand side ax, ay, az, right? So therefore equating ax terms, anything you can equate. You can equate ay, or you can equate az terms, right? So here I'm equating ax term, right? So equating ax term, we will get equation 2, right? And hy is the magnetic field component in y direction. The magnetic field component in y direction is in this form, right? Hy is equal to hy naught e power minus gamma z, and I am assuming that the wave is propagating in z direction, so therefore it is a function of z. And similarly hz, so this is hz is equal to hz naught. Hz naught is the amplitude, and e power minus gamma z. So here z, z means the wave is propagating in z direction, right? So e power minus gamma z component is common to all, right? So substituting these two in equation 2 and differentiating, right? So differentiating, we will get this equation, right? And further simplification, right? Further simplification, we'll get eta is equal to this one, right? And the gamma is this, substituting gamma here and simplifying, right? Simplifying. So simplifying, you will get eta is equal to root over j omega mu by sigma plus j omega epsilon. So this is the expression for intrinsic impedance, the general expression for intrinsic impedance, right? So um, um, free space, if you consider free space, sigma is equal to 0. So therefore if you substitute sigma is equal to 0 here, and we will get eta is equal to root over mu naught by epsilon naught, and which is equal to 377 ohms, or it is 125 ohms, right? So this is about intrinsic impedance of an EM wave, right? And up to here I have discussed in my last class. So let us move on to another topic. With this we have completed wave propagation, right? EM wave propagation in different media, 4 medias we have completed. Skin depth, right? Skin depth, so very important short answer question. Skin depth, right? So the skin depth, for example, this is the media, right? So this is one media, right? So let us say this is a dielectric media or a good conductor, whatever it may be, right? So when EM wave incidents, when EM wave incident on this media, right? So this is a medium, right? When EM wave incidents on this media, to what depth the EM wave penetrates, to what depth EM wave penetrates into the let us say this is a conducting media, right? And as we know that inside the conductor the field is zero, right? It does not field does not exist inside a conductor, right? Because conductor conducting surface reflects EM waves, right? Conducting surface reflects EM waves, right? So therefore to what depth the EM wave can penetrate, up to what depth EM wave can penetrate through a conducting media is called as skin depth, right? Is called as skin depth, right? So up to some extent it can penetrate, right? Up to some extent it can penetrate through the media, right? So up to what extent it penetrates, that depth, right? That depth is called skin depth, or skin depth, or it is also called as depth of penetration, right? Depth of penetration, right? So it can be defined as the it is a measure of the depth to which an EM wave can penetrate the medium, right? It is a measure of the depth to which an EM wave can penetrate the medium, right? Is called as skin depth or depth of penetration, right? So depth of penetration or skin depth, which is denoted by delta, right? Which is denoted by the symbol delta, is inversely proportional to the attenuation constant, right? It is inversely proportional to the attenuation constant. So delta is equal to 1 by alpha, right? Delta is equal to 1 by alpha, right? So this is the formula, and we can derive this formula, right? And we can also define like this. Skin depth we can define technically we can define skin depth like this. So let us say it is Z, right? So Z, if the wave is traveling in this direction, this is Z, right? This is Z, right? In this direction, wave is propagating in this direction, this is Z, right? So therefore this is Z, and let us say this is X, right? So when the wave incidents, right, when the wave incidents on the surface, let us say this is the surface, then the let us say the amplitude of the wave is E naught, right? Amplitude of the wave is E naught, right? When it instants on the surface of the media and uh, travels, in other words penetrates, right? Penetrates in right? So welcome back, right? So the wave is traveling in z direction, right? So this is right. So this is the z direction, right? So wave is traveling in z direction when it travels a distance delta, right? Delta is skin depth, right? Then the wave's amplitudes, the wave amplitude will reaches to 1 by e times e naught, right? The wave, the wave's amplitude reduces to 1 by e time e naught, right? So that means the wave's amplitude reduces by 37%, right? The wave's amplitude, um, okay, is my voice, is it okay now? Is my voice okay? Is it audible now? Someone is saying that my voice is very low. Please verify and respond to me. Right, thank you. Right, so 1 by each time, that means 0.37 e naught, right? 1 by e times e naught in the sense 0.37 e naught, that means 37%. When wave amplitude reduces to 37% of its original amplitude, right? Its original amplitude, and that is called as skin depth, right? So therefore at this distance, right, at this distance, the wave's amplitude is reducing by 37%, and that distance is called as skin depth, right? And as we know that wave can be represented like this. Earlier we have seen, right? So ey is equal to ey naught e power minus gamma z, right? So this is how we can express electric field component, right? Electric field component in phasor form like this. So therefore e power minus gamma z. So what is e power minus gamma z? E power minus alpha plus j beta z, and this is equal to e power minus alpha z e power minus j beta z, right? We can write like this, right? So here, as we know that any wave can be characterized with amplitude and phase, right? Any wave, right? Any wave can be characterized with amplitude and phase. How amplitude is varying and how phase of the wave is varying, right? So here, this term e power minus alpha z will give you the variation in amplitude, right? Variation in amplitude, and the second term, so this term will gives you the variation in phase, right? How amplitude of the wave is varying and how phase of the wave is varying, right? So therefore from this we can say that the first term is amplitude, right? That means e power minus alpha z is amplitude, right? At z is equal to delta, which is called skin depth, right? At z is equal to delta, um, e power minus alpha delta is equal to e power minus 1, right? So as we know that at z is equal to delta, the wave amplitude reaches to 1 by e, right? The wave's amplitude will become 1 by e. 1 by e in the sense what? E power minus 1, right? So therefore e power minus delta is equal to e power minus 1. So therefore we can write alpha delta is equal to 1 and delta is equal to 1 by alpha, right? So therefore, the skin depth or depth of penetration is 1 by attenuation constant, right? So skin depth is equal to 1 by attenuation constant, right? And let us consider a case, right? For good conductor, right? For good conductor, so if you consider a good conductor, delta is equal to 1 by root pi f mu sigma, right? Delta is equal to 1 by root pi f mu sigma, because alpha, so what is alpha for a good conductor? In the last class I have discussed alpha, so this is alpha, right? So alpha is equal to root over pi of mu sigma for a good conductor. So therefore, substituting that expression, we will get delta is equal to 1 by root over pi f mu sigma, right? So this is about skin depth or depth of penetration, right? So this is one uh, short answer question which is very important, right? And let us do some related problems here. Right. In a, note it down, in a lossless medium, for which eta is equal to 60 pi, mu r is equal to 1, and h is equal to minus -zero point 0.1 cos omega t minus z ax bar plus 0.5 sin omega t minus z ay bar amperes per meter. Calculate epsilon r, omega, and electric field component. Right, very important model. So once read out the problem carefully. In a lossless medium, right? So lossless medium, lossless medium. So lossless medium is characterized by what? Sigma is equal to 0, mu is equal to mu naught mu r, epsilon is equal to epsilon r epsilon naught, right? So these are the characteristics of a lossless dielectric media, right? And it was given that eta is equal to 60 pi and mu r is equal to 1, right? Mu r is equal to 1, right? And h is equal to h is equal to um, h x naught cos omega t minus beta z ax bar plus h y naught sin omega t minus beta z a by bar, right? So the given magnetic field component is in this form, right? Is in this form where hx naught. So what is hx naught? Hx naught is the amplitude of magnetic field in x direction. Hy naught is the amplitude of magnetic field in y direction, right? In y direction. So hx naught is as per the given equation, hx naught is equal to just a minute, there is some problem. Okay, right? So wave is propagating in z direction, right? Wave is propagating in z direction, right? And beta beta is phase constant, right? Beta is phase constant, right? So in fact it is gamma alpha plus j beta. So we have beta means what? Alpha is equal to 0, right? Alpha is equal to 0. So we have only beta, right? So therefore from the given equation we can say that beta is equal to 1, right? From the given equation we can say that beta is equal to 1. Here omega t minus z, omega t minus beta z, beta. So what is beta? Beta is 1, right? So this is the given data which we have, right? So we need to determine epsilon r relative permittivity, and omega we need to determine, right? And we need to determine electric field component, right? And as we know that intrinsic impedance eta is equal to root over mu by epsilon, right? And this is equal to root over lossless media, right? So therefore mu r mu naught by epsilon or epsilon naught, and this is equal to 120 pi root over mu r by epsilon r. And mu r is given, eta is given, mu r is given, and we can determine epsilon r easily, right? So eta, so what is eta? 60 pi, right? 60 pi is equal to 120 pi is equal to 1 by epsilon r, right? Eta is given, eta is given, and mu r is given. So substituting those values here and simplifying this, we will get epsilon r, right? So epsilon r, if you calculate epsilon r, you will get 4, right? We'll get 4. And similarly, this is how we can determine epsilon r. And similarly, we can determine omega from this expression. Beta is equal to omega root mu epsilon, right? So this expression we know, right? So it is a lossless media, right? So if you go back to the lossless media, this is lossy, and here, right? If you go back to the lossless media, for a lossless media, what equations we know? We know this one, right? So beta is equal to omega root mu epsilon, right? Omega root mu epsilon, and eta, right? Eta is equal to root mu by epsilon, right? So we are using those formulas, right? Related to lossless media, we are using those formulas. So coming back to the problem, beta is equal to omega root mu epsilon, and we need to determine omega, which is equal to beta by root mu epsilon, right? So beta is 1, and root over what we can write, mu r mu naught epsilon naught, right? So this is equal to 3 into 10 power 8 divided by root 4, right? Since 1 by root mu naught epsilon naught is equal to 3 into 10 power 8, right? And mu r is 1, epsilon r is 4. Substituting these values which we know, right? And simplifying, right? If you simplify this, you will get omega is equal to 1.5 into 10 power 8 radians per second, right? So this answer you will get, right? So therefore we have determined epsilon r, and we have determined omega, and we need to determine electric field, right? So how we can determine electric field? If h is given, right? We know h. And how we can determine electric field? Is there any relationship between E and H? Yes, we have. So what is the relation? Eta is equal to E by H, right? Eta is equal to E by H, right? So therefore E is equal to eta H, right? E is equal to eta H, right? So from this relation we can determine, right? And this is one method, right? Method 1, to determine electric field. If magnetic field is known, we can determine electric field. And another method we have, right? Another method we have, that is from Maxwell's equation. So one of the Maxwell's equation which we know, del cross H is equal to sigma E plus epsilon dou E by dou T, right? So for a lossless media, for a lossless medium, sigma is equal to 0. So therefore del cross H is equal to epsilon dou E by dou T, right? So from this we can write dou E by dou T is equal to 1 by epsilon del cross H, and E is equal to 1 by epsilon integral del cross H dt, right? So this is the equation how we can determine electric field. If H is given, we can determine electric field, right? So let us say this is equation 1, and determine del cross H, right? Determine del cross H and substitute, simplify, you'll get the answer. What is del cross H? Ax bar, Ay bar, Az bar, dou by dou x, dou by dou y, dou by dou z, x component, y component, and z component, right? So this is equal to Ax bar, Ay bar, Az bar, dou by dou x, dou by dou y, dou by dou z. So what is x component? So this is the x component, right? So this is the x component, this one. So this is the x component, and this is the y component, and z component is 0, right? So there is no z component, right? So therefore we can write x component is minus 0.1 cos omega t minus z, and y component 0.5 sine, right? Sine omega t minus z and 0, right? Z component is 0, right? So find out the determination here. So we know how to find out the determination, right? So if you determine, right, if you calculate this, you will get 0.5 cos omega t minus z ax bar minus 0.1 sine omega t minus z ay bar. This you will get, right? So this is del cross H, right? So substitute del cross H. Substitute del cross H where? In this equation, right? Substitute del cross H and integrate, right? And integrate, you will get E, right? So E is equal to 94.25 sine omega t minus z ax bar plus 18.85 cos omega t minus z ay bar volts per meter, right? So this is the answer, right? So this is how we can determine, right? So this is one important model. Almost all the problems will be like this only, right? So they will give the media, and they will give electric field or magnetic field, and they will ask you to determine some parameters like epsilon or omega, and sometimes beta, right? And electric field or magnetic field, like that they will ask you to determine, right? So with this, let us close our session. It is already 10, right? So thank you very much for your patient listening. Is it clear? Today's class, is it clear? Please respond. Is it clear, today's class? Please respond, because today we have some technical issues, right? Okay, thank you. 418, 406. And we will meet you on Monday, right? Because tomorrow and day after tomorrow you don't have classes because of online tech fest, right? And we will meet you. We'll meet again on Monday, right? So thank you very much. Now you can leave.